aspect is to determination of the electron charge to mass ratio, and my advisor is Dr. Hongtao Xi. So as Dr. Xi mentioned earlier, the measure of E over M ratio using the Pascal apparatus in the physics 216 is always greater than the predicted value. So my goal is to find out what causes this experimental error. This is the outline of my speech today. So first, including the brief history of how British scientist G. Thomas measured the E over M ratio and how he used this method to find the electrons, followed by the experimental setup and the parameters we measured, and the improved method with the, and followed by some discussion about the data we separate, and ending with the conclusion. Back to the 1897, British scientist, physicist G. Thomson using the cathode ray tube to measure the E over M ratio, and based on this experiment, he becomes the first person to find the electron. For Thomson's approach, he using a so this is the Thomson's approach. He's using a cathode to accelerate the light beam, and the electron beam is deflected the electric field, and the Thomson had a B field, the magnetic field perpendicular to the electric field to neutralize the beam go a straight path. And the established E over M ratio he measured is 1.76 times 10 to the 11th coulomb per kilogram. The Pascal approach which we use to do the experiment today is we use the separately magnetic field and the electric field so that we can observe a light emission ring that we can measure the radius of the ring in order to get the ratios of the E over M. This is the experimental setup for our experiment. On the left side is Pascal E over M apparatus we use to measure the radius of the light emission ring, and we use a Pascal high voltage power supply to accelerate the electrons and the filament heater. And the GW power supply is using to produce us a magnetic field out of the Helmholtz coils. And we also use a digital multimeter to measure the current in order to calculate the E over M ratio. The theory behind this experiment is pretty simple. So first, the electrons is gain the kinetic energy due to the potential energy lost. And based on the Newton's second law, we can rewrite the equation 1 to this form. This is because this is demonstrate how the electron path can form a light emission ring, and combine those equations together, we count out the equation we're going to use to calculate the E over M ratio. Notice that this equation involves the acceleration voltage on the top, and also the ratios of the light emission ring and the magnetic field. The accepted value for E over M ratio is, as I mentioned earlier, is 1.76 times 10 to the 11th coulomb per kilogram. Next, I'm gonna introduce the parameters we measured. So first of all, we using we need to make sure, we need to confirm that the light emission ring is caused by the helium atom. So we use the Ocean Optics USB 2000 spectrometer to measure the light emission. And the range of the spectrometer is from 200 to 1100 nanometer with a resolution of 1 nanometers. And we also use a ruler to measure the radius of the light emission ring. We use the field sensor and the data studio as the interference to measure the magnetic field. This is the picture for the setup. I also did some improved method to get those data more precisely. First, I add a slider on the ruler to get a better measurement of the radius. Secondly, I separate the magnetic field sensor before each measurement. And also, I use a level to level the system, including the field sensor. So, as I mentioned earlier, first we need to make sure the light ring is caused by the emission of the helium gas. So this is the picture shows how the light emission ring looks like in the apparatus. We can clear to see a green color ring here. After I using the spectrometers in different voltage to measure the spectrons. First, I apply a 200 volts and also a 250 volts. In different voltage, they give us exactly same peaks of the spectrons, and those peaks perfect. If we go back to the chart of the helium wavelengths, those peaks perfectly match the peaks of the helium. So notice that there's a huge peak on 500 nanometers. This is the reason we can observe a cyan colored ring. And also keep in mind that there is 470 nanometers peaks right behind the huge peak. This is the peak I'm going to use later to demonstrate the light emission in a quantum mechanics model. The data I show here is the student, the primary data we use without any adjust or modification. So this is the general data we're going to get if we didn't use any improved method. So we can find out that there is a huge experimental errors here. It's like almost 60% of the theoretical EOM ratio. And, that is because the magnetic field given from, we use the magnetic field value given by the manufacturer, which is 7.8 times 10 to the negative 4th in Tesla. So I'm thinking if there is something wrong with this number, so that's why I used a magnetic field sensor to measure the magnetic field. After I separate the magnetic field, I find out that actually the magnetic field is a linear correlation due to the changing in current. So the coefficient is about 7.29. So which is obviously much lower than the 7.8 given by the manufacturer. With those improved, I improved the method to measure the radius and also the magnetic field. With those improved method, I find out it gives out bring down the experimental error to 30 to 35%. Notice that under a higher voltage here, we're gonna get a better EOM ratios. However, we already discussed, there's still a 30% to 35% experimental error, even we improve the method to get a better radius and magnetic field. So the only thing possible to responsible to this error is the remaining is a certain voltage. Well, back to the light emission process, the concept between this is each helium atom has 2 electrons orbiting around the nucleus, and one of the electron ionized, the other one have to jump from a higher energy level to a lower energy level. This process will produce a light photon. That is the reason we observe the light emissions. So under this concept, we use the equation from the quantum mechanics to calculate how much energy we use cause these emissions. So I calculate this using this equation. I find out the first ionization energy, which it is 24.6 volts, which is the first electron to ionize. And I assume that this is the energy we're going to lose in this process. So I add these parameters to my calculation. I find out I'm trying to see if it will give us a better result. So after I put these parameters to calculate this, I got still 20% experimental error. So then, which means this is not enough to explain the total voltage, the total energy is consumed. So I start to think about the second ionization, which is energy required for the second electron to get ionized, which is 54.4 volts. Use this as an example. For example, an electron fall from the fourth energy level to the third energy level. It will require 2.64 volts. And this is the example I mentioned earlier, that the wavelength is matched one of the peaks of those spectrum we measured, which is give us a blue color of the peak. So for this example, if an electron from the ground state to the fourth state requires about 50 volts to energy to get ionized. So I add the 50 volts as a parameters in this determination. So it brings down our percentage error to 4%, or 4.7%, or 4.8%, which is more meaningful to us. And as a conclusion, first, I got a better radius measurement after adding a slider to the rulers. And secondly, I use a magnetic field sensor to find out that the magnetic field is linear dependent on the current, and it gives us a linear coefficient, which is 7.29 times 10⁻⁴, which is much smaller than the value given by the manufacturer. Third, the light emission observed in this experiment is caused by the ionization of the helium gas. And we can expand this in quantum mechanics model. And lastly, the part of the electron kinetic energy is transferred to helium and causing the ionization. The measured velocity is much smaller than the predicted value. Thank you so much.